Hello students, I hope you are having a wonderful day. I would like to complete another practice problem with you from chapter 2, and it's titled The Two Cars. So let's go ahead and get started. The graph below shows the position time graph for two cars traveling on a straight highway. So right here we have the position time graph, and just for clarity, what I've done is I have labeled car A, the position and the time for car A, and car B, and I have also labeled the ordered pair right here for car B. Right here we have the X value 7 hours and the Y value, the position is 150 kilometers with respect to the origin. Okay, so on number 1, what does the slope of the line on a position time graph represent? So right here on our position time graph, the slope of the line is identified by lowercase m. We know that it is rise over run, so delta y divided by delta x. Remember, the Greek letter delta is change in, so the change in y, we have y2 minus y1 divided by x2 minus x1. And so right here, what I really want to do is just focus on the units. So in my numerator, I have kilometers, and in my denominator, my x value, right here, we have hours. So kilometers per hour, this is a unit of velocity. So what does the slope of the line on a position time graph represent? It represents the object's velocity. Now remember that velocity is a vector, not a scalar, it's a vector, so it will show magnitude and direction. And I'm going to add that here. So, shows magnitude and direction. Okay, moving on to number 2. What can you determine about the relative direction of the cars? So let's take a look at car A. So for car A, we can see that it has a negative slope. Okay, so since it's a vector, we know that the car is moving in a negative direction. But I'm going to write negative slope. So this is going to equal, it's moving in a negative direction. Okay, now let's take a look at car B. So car B starts from the origin at a time of 0 hours. We're at a position of 0 kilometers. And then at a time of 7 hours, we are at a position of 150 kilometers. And you can just visually see that we have a positive slope. And remember, velocity is a vector, so not only can we calculate the magnitude of the velocity, we can also know its direction as well. So this is moving, car B is moving in a positive direction. Okay? So on number 3, what time do the cars pass each other? Well, what we want to do is first identify the relationship for each car, car A and car B, on this position time graph. And we can see that we have a linear relationship here. So it's going to fit the slope-intercept form, which is y equals mx plus b. Okay? So first, let's take a look at car A. For car A, right here, what we need to do is first calculate the slope. Now, we have our equation for slope given right here. So y2 is going to be 0 kilometers. So car A starts here. So y1 is here, y2 2 is here. So we have 0 kilometers minus, now we have an initial position here of 450 kilometers. And we're going to divide this by x2 minus x1. So x2 is 7 hours. x1 is 0 hours. Okay, and x, so x represents our independent variable. And in this situation, we're looking at a position time graph. Our independent variable is time, so I'm going to use lowercase t, plus b represents our y-intercept, and our y-intercept is 450 kilometers. Okay, and so let's get out our calculator here. Let's do 450 kilometers divided by 7 hours. I'm sorry, we're going to have a negative in the numerator, so negative 450 kilometers divided by 7 hours. I get negative 64.29. So my equation, I'm going to have negative 64.29 kilometers per hour multiplied by t. This is our independent variable, plus 450 kilometers. Okay? Now for car B, once again, we're going to put it into the slope-intercept form. So y2, so here's y1. Here's our first ordered pair, our second ordered pair. y2 is 150 kilometers minus 0 kilometers. Then we have x2 minus x1. x2 is 7 hours. Minus 0 hours. Okay? So 150 divided by 7, I'm going to get 21.43. Well, we have t, and then we have right here a y-intercept of 0 kilometers, but since it's 0, we don't even need to write that. So I have a positive 21.43 kilometers per hour multiplied by time. Okay? Now what we're going to do is set these equations equal to each other, and then we're going to solve for our unknown variable t. This is where their paths are going to cross. At what time? Okay? So I'm going to rewrite this. I have negative 64.29 kilometers per hour multiplied by time, plus our y-intercept, 450 kilometers. We're going to set this equal to 21.43 kilometers per hour multiplied by t. And so what we want to do here is, we know just by looking at the graph where they cross, and this is known as the point of intersection. So we know the point of intersection, the x value, is somewhere between 5 and 6 hours. But we don't want to say, well, it's somewhere between 5 and 6 hours. That's a huge range, and we definitely want to be much more accurate than that. So that's why we are solving first for the x value point of intersection by setting the equations equal to each other. So what I can do right now is I can subtract 450 kilometers from both sides of the equal sign, and also subtract 21.43 kilometers per hour times t from both sides of the equal sign. So what I have is negative 64.29 kilometers per hour t minus 21.43 kilometers per hour times t is equal to a negative 450 kilometers. Okay? Now, the reason that I did that is because we want to combine like terms. Okay? And so right here, let's do negative 64.29 minus 21.43. And this is going to give me negative 85.72 kilometers per hour times t is equal to a negative 450 kilometers. Okay? Now what I want to do to solve for t is divide by negative 85.72 kilometers per hour on both sides of the equal sign. And let's just talk about the numerical value first here. So we know that on the left-hand side of the equal sign, this is going to cancel, okay? Now, what you do to one side, we have to do to the other to keep it balanced here. Negative 85.72 kilometers per hour. So all of this is going to cancel. We have a negative divided by a negative, so this is going to give us a positive time. So 450 divided by 85.72 is equal to 5.25. Okay, now let's take a look at the units here. So in our numerator we have kilometers, and algebraically we can write this as kilometers over 1 divided by kilometers per hour. And remember, whenever we divide fractions, it's like multiplying by the inverse of the denominator. So what I have is kilometers over 1 times hours over kilometers, okay? And you see right here, the units of kilometers are going to cancel, leaving us with units of hours. So our two vehicles, A and B, cross at a time of 5.25 hours. So at what time do the cars pass each other? I'll just say time equals 5.25 hours. And that is our answer for number 3. Okay, number 4. At what position do the cars pass each other? So right here we have our point of intersection. We've already calculated, we solved for the x value of what time, and I'll just go ahead and start an ordered pair here. We have 5.25 hours. We don't know the x value, we don't know the y value yet. We can look at the graph here, and it's somewhere between a position of 100 and 150 kilometers, it looks like. But once again, we definitely need to be more accurate about that. So what we want to do is we can use any equation here, and we can, for our cars, to plug in this 5.25 hours, okay? And so what I'm going to do, we can use either one because the y value will be the same on both of them. Let's go ahead and plug it into this one for car B. So we have 21.43 kilometers per hour, okay? The unknown value here, time, we're going to plug in this value, 5.25 hours. And let's take a look at the units here. My units of hours will cancel, leaving me with units of kilometers. So 5.25 times 21.43 is going to give me 112.5 kilometers. And that is the position that they cross, okay? So our point of intersection for these graphs is 5.25 hours, 112.5 kilometers. Okay? And our last question here. Which car is traveling faster? Well, what we're going to do is take a look at the slope of the line. Now, the slope of the line on a position time graph represents the object's velocity, but the absolute value of the slope of the line on a position time graph represents an object's speed. Now, this is magnitude only. It's not showing direction. So, and let's write this down just to kind of help remind us. The absolute value of the slope of the line on a position time graph represents the object's speed. Okay, and I'm going to underline that because speed is a scalar, okay? So it's only magnitude. We're not showing direction at all. So which car is traveling faster? So you could also word that is like which car has the highest speed, maybe. So right here, the absolute value for car A would be 64.29 kilometers per hour. The absolute value here for car B, well, 21.43 kilometers per hour. So which car is traveling faster? Car A is traveling faster. Okay. All right, so please send me an email if you have any questions over the two cars problem. I hope you have a wonderful day.